About 14 billion years ago, an enormous amount of energy erupted out of a single point. In fractions of a second, that energy expanded in all directions, creating space and time as it moved. As the universe expanded, it cooled, and that raw energy began to convert into mass. This process is governed by mass-energy equivalence, the principle defined by Albert Einstein's equation E equals mc squared, which shows that energy and mass are two versions of the same thing. The laws of physics require symmetry. When energy converts into mass, it must split evenly into matter and antimatter. Antimatter has the same mass as ordinary matter, but an opposite charge. If they touch, they instantly annihilate, converting their mass back into pure radiation. If the universe created exactly equal amounts of both, every particle should have found its opposite and destroyed itself. Mathematically, the cosmos should be a cold, empty void, containing nothing but leftover light. However, the visible stars and galaxies of the Milky Way prove otherwise. We see heavy elements, orbiting planets, and complex biology. Because solid mass exists today, a strict physical law was broken in the first moments of expansion. The universe is heavily lopsided, and locating the missing antimatter is one of the most persistent questions in physics. To solve this, many physicists use the Standard Model, the framework describing how the fundamental forces of nature interact. According to this model, the fate of our reality was decided within the first 3 minutes of creation. During that high-density phase, the universe produced a microscopic imperfection. The symmetry was not perfect, resulting in a tiny fraction of extraordinary matter compared to antimatter. The imbalance was minute. For every 1 billion particles of antimatter created, there were 1,000,000,001 particles of matter. This led to a period of total annihilation. The billions of paired particles collided and converted back into radiation, leaving only the single, unmatched particles of matter behind. That tiny leftover fraction of matter survived as the universe cooled. Over billions of years, those particles clumped together to form every galaxy, star, and person that exists today. In this view, human existence is simply the leftover material from a nearly total cosmic destruction. But an alternative hypothesis proposed by physicists like Arya Tanmay Gupta suggests a different timeline, one where matter and antimatter never actually collided. This idea relies on the law of conservation of momentum. To maintain a balanced system, Gupta suggests the primitive universe broke into two separate halves that never interacted. Instead of mixing, the mass of matter and the mass of antimatter repelled each other with immense force. One of those halves became our observable universe, a reality made entirely of ordinary matter, expanding outward from that initial separation. The other half is the anti-universe. It is a mirror reality made of antimatter, moving in the exact opposite direction at a speed greater than light itself. This hypothesis resolves the symmetry paradox through isolation. The balance of physics remains intact, but the two halves are separated by a growing void we can never cross. These two models represent the primary ways we try to understand our history. We are either the leftovers of a microscopic imbalance, or we are one half of a hidden twin universe. Identifying where the missing antimatter went remains a primary goal for modern physics. Science must continue to follow the evidence. Researchers are searching for either the faint radiation signatures of the Standard Model's annihilation or the repulsive forces required by an anti-universe. Stephen Hawking suggested that finding the answer to the universe's origin would allow us to understand the starting conditions of reality itself. It provides a complete physical history of our existence. Whether the answer is a microscopic leftover or a distant mirror, our presence today confirms that the early universe was not symmetric. It is functional because it is unbalanced.